how does this milky tree juice relate to Formula One? A good question. People do really be milking everything these days. They're milking almonds. They're milking cashews. Soy. Rice milk. You know, I think almonds pretty good. Soy's like terrible. Cashews, okay. What about trees? Ever milk trees? Some tasty white tree milk? Probably not the best thing to have in your latte. So this milky white fluid is known as latex, which is coming out of a tropical rubber tree. Delicious. So what is the chemical in this liquid? It is cis-1,4-polyisoprene. Okay, I see you. You're cis. You're white. Must be nice. Or in other words, this is referred to as natural rubber. Oh, okay, rubber comes from a tree. Did you know that? I didn't. So what is rubber? Rubber is an elastomer, or an elastic polymer. Elastomer. Very cool name. So the polymer part means really long molecules made up of repeating units of the same like building block. So you just repeat that over and over again, connect it all in one big line, polymer. So elastic, what does that mean? That means in its natural state it's all curled up. You can apply a force, like pulling it, stretch it out really long, and then when you release, it can go back to that curled up state. Cool, elastic. So I was talking about that they're made of these little building blocks, right? So the building block of natural rubber is isoprene. So there she is, right there. Beautiful. You connect up a bunch of these bad boys together. Polyisoprene. Okay, so I did say it was cis. What does that mean? That means the connecting bits in the polymer are on the same side of the double bond. So that means it's going to form a nice straight long line. As opposed to trans, which means it would be on the other side. Be like a diagonal. Not fun. Okay, wow. So a tree makes rubber. Crazy. But what if you don't have a rubber tree just chilling in your backyard? So these scientists, Ziegler and Natter, came up with a fun process to synthetically convert this isoprene building block unit into polyisoprene. Cool. How do they do that? What they use is a titanium catalyst. Ooh, okay. Okay, it's cool. You guys know what a catalyst is, right? You did chemistry in high school. Catalyst speeds up the reaction. Yeah, you got this. Okay, so how does this work? You start off by activating this titanium catalyst. So you're adding a little carbon group on, and then on one side of the titanium, he's lost his friend. Oh no. He's got an empty d orbital just chilling there, and he's a bit sad, and he's like, come on guys, I just want some electrons in this orbital. I'm a transition metal, come on, fill me up, give me some electrons. So that's where the isoprene, the building block, comes along. Swimming along. It's like, hey girl. Hey titanium, how are you? Titanium's like, bruh, can I have some of your electrons? And isoprene's like, sure, I got like a double bond. There's electrons in there that I can just share with you. Titanium's like, great, thank you so much. Now I have some friends. So the isoprene coordinates to the titanium. Perfect. So now when they're together, coordinated, this is where chemistry can happen. Woo. So the isoprene says to the titanium catalyst, like, you've got some bonds, I've got some bonds. What if we just like switch them for fun? Titanium's like, oh yeah, okay, let's go, let's roll. So they form this 4-membered transition state. If the bonds are like this way, then all of a sudden they go whap, and just switch the bonds around for fun. And by the process of doing this, the carbon chain that was originally on the titanium has managed to jump across and be on the isoprene unit now. Cool. So you've just extended the isoprene unit's chain. Okay. And the process of this has opened up a new empty d orbital on the titanium. Sorry titanium, you just filled it up and now you've lost him again. But not to worry. Another monomer of isoprene can swim along, and it can be like, hey, don't worry, I can coordinate to you. So that can coordinate, do this 4-member transition state again, and then be connected onto the original chain. So this keeps happening over and over and over again until you've extended this chain really long, and it becomes a polymer. Wow. And the final step, the termination, you can just cut the titanium off, be like, bye girl, thanks for your help, I'm out now. And there you have it, polyisoprene, made synthetically. Cool. Instead of just copying the tree straight away and using isoprene, why don't you use something else? use styrene, butadiene, other chemicals. And by using these different starting blocks, you can adjust the properties of the rubber at the end. Maybe it'll change its heat resistivity. It'll change how elastic it is. Maybe it'll change what it smells like. You know, all these things. So by changing these starting blocks, you can optimize how your rubber is at the end. Wow, these chemists be slaying. So back in the 19th century, they were taking this rubber from the tree, thank you tree, and thought, okay, cool, let's try to make a tire, put on our cars. How was it? Not very good. Just using this raw rubber, it gets very sticky if it gets hot. It can pick up the debris on the road. If it gets cold, it just doesn't work very well either. All around, not very stable, it's just not the vibe. So this guy, Charles Goodyear Tyres, named after him, not founded by him. I'll get to that. So Charles Goodyear, he comes along and is like, how can we make rubber a little bit better? He tried a bunch of different experiments. He was adding nitric acid, that kind of helped, didn't really. Trying a bunch of stuff. One point, he added sulfur to the rubber. Wasn't really do anything. He trips and knocks it into a hot frying pan. Ruh-roh. Don't quite know how that happened. And he's like, oh no, it's gonna like burn. But it didn't. He's like, okay, we'll leave it there. We'll see what happens. Just heating up some rubber and sulfur together. And what does it do? Magically, it makes the rubber more durable, more stable, more rigid, be able to withstand better temperature differences. He's like, wow, it's magic. I've solved it. How did I do it? I tripped over and knocked it in a hot pot. So what he had invented is the process of vulcanization. Ooh. Okay, so what's actually happening here? We already found out that rubber is a long chain molecule. So there's a bunch of these chains, but they're not connected to each other. They're just kind of slipping all over the place. And that was one of the problems of why rubber wasn't the best material. However, when you add sulfur and heat it up, the sulfur can insert between two chains, the wrapper, and can form these cross-linking bridges between the two polymer molecules. Wow! These chains are chemically bonded through sulfur and they're a lot more stable. A good analogy of the vulcanization process is if you have spaghetti, you can just take the raw spaghetti out of the packet, put it back in, you can pick up individual pieces. So this is like the polymer. There's a bunch of long molecules, you can just pick them up, they can move all over each other, not what you want. However, if you put it through a heat cycle, such as cooking the pasta and cooling the pasta, what happens is now the pasta is nice and sticky and it sticks together. So this is sort of what's happening to the rubber. Spaghettification. That's a different thing. That's to do with black holes. Maybe I'll do a black hole episode, wouldn't that be fun? Do I know much about black holes? Like a little bit, not a whole lot though. I know if you stand next to one you get spaghettified. This vulcanization process turned rubber into something that wasn't very usable into an incredible material that is now used everywhere. So this Charles Goodyear guy must be pretty famous, must be pretty rich. No. I don't know if he was just like a bad businessman or something, but he kept having to go to court and he was in like so much debt and he went to prison because he was in debt so many times. He ended up dying $200,000 in debt, which is like over, I don't know, $1 million or something in today's money. So yeah, sucks to be him. A cool invention. He didn't profit anything off it though. So the Goodyear Tire Company is named after him who invented it, not founded by him, so he's got nothing to do with it. So since the invention of vulcanization, there's been more advances on how to like deliver the sulfur. You can use like a sulfonamide or like another thing that can put the sulfur in, and then you can tune how much sulfur that you want. So that'll change the properties if it's, I don't know, more stable or less stable or different elasticities. I'm so excited, I get to use this as a prop. Oh wow, we got a Formula 1 car here. This is the W11. This is Lewis Hamilton's World Championship winning car from 2020. Meow. And as you can see here, it in fact has tyres. I told you this would relate to Formula 1. We're getting there. These tyres here, what are they made out of? A lot of different things. There's over 150 ingredients in the tyre. Do we know what these ingredients are? No, it's a secret from Pirelli, so they don't tell us anything. What I did manage to find is that there's about 10% natural rubber from the tree, And then the rest of the tread is different amounts of synthetic rubber. So as you can see here, the tyre, it looks a little different to a regular car tyre. Yes, there are no grooves in it here because this is a slick tyre. And the reason they use tyres like this is to have the maximum amount of rubber contacting the track at one time. So the contact patch, the patch of rubber that is touching the track at any point in time, because rubber is an elastomer, elastic, can deform a bit, so you get like a flat contact patch where the track is. So where the tyre is touching the track, it is actually molecularly adhering, so you're forming chemical bonds between the tyre and the track, and that is providing the grip. So you want a lot of area of tyre touching the track, because that's going to increase the amount of grip that you can have. So when the tyre is in contact with the track, spinning around, there's going to be friction there, and that generates heat. And there's a specific temperature window where the tyre performs optimally. So this is around 100 degrees Celsius. You can see a little graph here. Increasing the temperature, the grip increases to a point, but then if you keep increasing the temperature, you eventually lose grip. So allowing the rubber to get to the right temperature allows it to deform a lot more, and therefore you have more contact with the track, more grip, go faster, very good. If you get the tyres too hot, they're going to wear a lot faster, maybe have some blistering where some bubbles form, and it's just not the vibe. Interestingly, the tyres that are provided to Formula 1 are initially not vulcanized completely. So the drivers have to kind of do a little bit of vulcanization themselves. So you hear that the drivers want to put their tyres through a heat cycle. As we talked about this spaghetti heat cycle, heating it up, cooling it back down, this is allowing the vulcanization process to occur. So you can see on the graph here, when you first come out of the pits and start driving, you don't have the maximum amount of grip straight away. It takes a bit of preparation to have the tyres performing at the optimal grip level. So one thing that makes Formula 1 very exciting is the different strategies the teams can have when it comes to tyres. Throughout the history of Formula 1, there's been a bunch of different companies that make tyres, such as Goodyear, as we said before, or like Michelin, or Bridgestone, and now it's Pirelli. So these tyre manufacturers used to just bring their tyre, and then that was the tyre that you used for the race. Since 2016, where Pirelli is the tyre manufacturer now, what they bring to a Grand Prix weekend is 3 different types of dry tyre. A soft, a medium, and a hard tyre. Oh, and this makes it very exciting because the teams have to strategize what tyre they're going to choose and when. So they have to run 2 out of the 3 compounds available. So what's the difference between these compounds? As we said, we don't really know because Pirelli have kept it a secret, but there could be differences in the percentage of what rubber they use, like natural rubber versus synthetic rubber, or like what sort of synthetic rubber. They can change the amount of vulcanization, have it more vulcanized or less. They can have additives such as carbon black or silica, and this can change a bunch of factors such as traction or the rolling resistance, the resistance to roll. So the result of changing all the ingredients in the tyre, so there's a hard tyre which is designed to be very durable, last a long time, but provide less grip, so it's slower. On the other hand, there's a soft tyre which degrades a lot faster, but it provides a lot more traction, and therefore you can go a lot faster on the soft tyre. And then there's a medium which is a mix between the two. So what's interesting about the development of these 3 different tyre compounds that Pirelli brings, the soft, the medium, and the hard, is that they require different preparation and have different temperature windows to reach their optimal performance. So a driver has to change their driving style to get the most out of a tyre, and the strategists have to decide when it's best to use what tyre and when. So it's pretty wild. They've gone from having natural rubber, just taking it from a tree, putting it on cars, it didn't really work, too sticky, wasn't very good at temperature changes, to now having over 150 different compounds in a Formula 1 tyre and changing the tyre composition by different vulcanization techniques, different polymerization methods, and then different additives, which results in more exciting racing due to the different strategies that teams can apply now. Wow! See, I told you it related.
Oh hey, here I am, post-Bahrain Grand Prix. I was kind of hoping there would be some fun like tyre strategy thing that I could talk about, like, oh yes, Pirelli bring these different compounds that results in a cool strategy that teams are fighting over, oh, who's going to win? The person who chose the best strategy because of these different tyre compounds. But no, No amount of tyre strategy is going to help when Max is over 20 seconds in the lead. Yes, a bit depressing. So that's the championship over. Cool. So Red Bull have made a rocket ship. Mean. Love that. It really seems like Max could have put any tyres on his car. He could have put road tyres on and he still would have won. So, there's that.
Hey girl, hey, welcome to the outro screen. Hope you enjoyed the video. Hope you learnt about polymerization, vulcanization, Formula 1 tyres. Instead of an album recommendation, it's just a single today. It's a new 21 Pilots song. Woo! Called Overcompensate. It's incredible. I'm loving it. I love how they took some motifs from Trench and put it into this song. And it's like, welcome back to Trench. And I'm like, girl, I feel like I'm back in Trench. This is it. And then the tempo change is super fun. All around good vibes. What a song. Definitely recommend listening to it. Super excited for the new album, Clancy. It's going to be sick. Okay, bye.